Okay, you ready?
Hello, my name is Franklin Hu, and I am a dissident scientist. So this means that I may think of the way the world works in a little different way. Someone might call me a mad scientist. But don't worry, I'm not an evil mad scientist, hopefully. But I definitely have some different ideas. And so what I'm going to present to you here is an idea about what the neutrons and protons are doing in an atom. Now, I had this big, sophisticated, slick presentation that I was going to give to you, but since we are here at the conference, I want to interact with you guys. So I'm just going to give the briefest description of my idea, and I think a picture shows 1,000 words. So this is my idea of how the basic atoms work. Now the basic problem is that we know there's protons in the atom. And the question is, what keeps those protons from flying apart? And mainstream would say we have the strong force which holds those protons together. But that kind of begs the question of, well, we've got these neutrons in there. If it's a strong force that holds the atom together, what's the neutron for? It seemingly doesn't serve any purpose. So I'm going to see if I can paint this simpler picture for you. So for me, everything is basically made out of positrons and electrons. And a positron is exactly like an electron, except it has a positive charge. And it is known that a proton contains 3 objects from scattering. And mainstream would say there are 3 quarks in there. They would also say that a neutron contains 3 quarks. I say that's a bunch of hooey. This is what I say. I say a proton is made out of 2 positrons and 1 electron. Okay, so that's 3 things. The net charge of a proton is net plus 1. Okay, so that's a proton. And now, what is a neutron? Okay, a neutron is just simply a positron and an electron, okay? So starting with that, we have to think about, okay, if we've got these 2 protons, what could we use to glue together 2 protons? Because they've got plus 1 charge each. They would repel each other. The simplest thing to do is just to put an electron between them. So you can take proton, electron, proton. If you model that, those 3 particles will stick together electrostatically. There's no problem with doing that. And I think I have my other little picture back here. So in this picture, I show my proton. The positrons are these 2 red circles, and the electron is this negative circle. And what's gluing them together is this big this big black circle, which is an electron. Now that would be a completely linear atom, you know, proton, electron, proton, but that's not a very compact structure. So if we throw another electron into it, then it can form a loop. So you have electron, proton, electron, proton. So this is the simplest way to glue protons together with just an opposite electric negative charge. So that's the simplest thing. So, but the thing is that electrons do not glue together protons. We think neutrons glue together protons. And what I'm thinking a neutron is just an electron plus a positron. So the neutron does have the electron that we need to glue together the protons, but we have this leftover positron that has to be taken care of. So what you would do is that all you do is just throw on 2 other electrons to kind of balance those 2 extra positive charges. So I'm going back to my picture here so that you can finally see what this looks like. So over here, this is like a Lego brick, we have the proton, so that's shown in red. And then we have the neutron, which is an electron and a positron, which is basically gluing together the other proton. And we have one slot left, which is this electron, which actually I don't think is tightly bound to anything. Because if you have a positron and electron, it will try and mate very closely with its opposite. So in the proton, you've got the elements in the proton closely mating with the neutron. So the protons and neutrons are glued together, and actually the electron is basically free. And this is why we can ionize off the electrons versus we can't ionize off, say, the protons. The electrons are free because they are technically not actually bound into any combination into the electron. So that's the basics of my theory. And so things like the strong force actually need not exist, that this is held together entirely with the electrostatic force. So do you guys kind of understand what kind of model I'm presenting here? I think it's pretty simple. Everything is just a combination of opposite charges. But what I want to do is spend the rest of the time is just kind of get your guys' objections or ideas or comments on this. So first I want to make sure everyone can hear me and can raise their hand. So can everyone raise their hand for me? Let's see here. Duncan, yeah, okay. All right, you're almost raising your hand, all right. So you've all proven that you can raise your hand, right? Okay, so as you're listening to this may be new to you. So you may think this might be plausible, or you might think this is true, or you might think this cannot be true. So I'm just wondering, are there any people here who have some reasons to think that this cannot be true? Yes, Duncan. Can you tell me what are some problems with this conception?
Your assertion is that there need not be a strong force to hold everything together. It may be electrostatic force. I assume by that you mean a strong electrostatic force.
No, just regular electrostatic Coulomb force.
All right. But that connotes there being a charge which has an attractive force to it.
That's correct, yes.
Okay. There have been a number of discussions, mostly not related to papers at this session, but over lunch, dinner, and so on, about the question of whether charges exist. And the question I have is in regard to strong force, but I'm going to accommodate you, translate that into electrostatic force, and ask whether an alternative approach may be that no force at all is required to keep the neutrons and protons together, not attached to each other, but together as entities. With this being the basis of it, that the protons and the neutrons are structures that are made of particles that are attached physically, mechanically attached to each other, the result of which is that in order to tear them apart, there has to be an immense force to actually break the physical connections. If that is the case, then it seems to me you have a situation where a great deal of force is required to actually break these connections. And it's not that we're dealing with a strong force that's holding these entities together. We're dealing with physical connections that are holding them together.
So it sounds like that's not particularly an objection to this one, but in fact an entirely new, different model. which is a little bit like this. I mean, my Lego bricks are literally held together, as you say, as a mechanical connection. I mean, if I were to build this thing out of Lego bricks. But that is not my model. But I'll give it to you that may be a possibility that the neutron has some kind of hook on it that goes onto the proton, and that's what keeps these things together, and that's why it's so hard to pull these things apart. I would say that, but like I said, that not really a comment on, say, this particular model. I was asking, do you have a objection on the plausibility of this model? But I totally acknowledge the possibility of your model.
And I take your point as well. Thank you.
Yes. Get a microphone. But like I said, I want to hear from you guys. I want to spend my time on my speech.
It's well known the proton is very, very stable, and the neutron is not.
Mm-hmm.
The way that you compose them would seem to make the neutron far more stable than the proton. Why would a proton, which is 3 particles, 2 of which are positive and 1 is negative, why would that be more stable than a positron and an electron?
Well, you must be referring to the fact we know that a neutron, once it escapes the atoms, has a half-life of around 15 minutes or so, which actually, for a subatomic particle, is like a gazillion years compared to everything else. It lasts a long, 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 long time. But within the atom itself, the neutron is completely stable, right? Not unless you're talking about radioactive elements, but that's a different question. But typically, if you have like a regular hydrogen atom, that neutron is as stable as the protons. It doesn't decay. Now, your question is, what is the difference? Why is the proton more stable than the neutron? And I would first of all say that it's not. Within the atom, the neutron is as stable as the proton. The question happens, well, what goes on? What's happening when the neutron leaves the atom? Now, that's a different subject, but I think I need to answer that, which is that when the neutron is ejected from the atom, it's still a positron-electron pair, just like here. But when it's ejected, it's actually ejected into a sea of such identical particles. That's another part of my theory, which says the ether is made out of, basically, you could call it a neutron sea, basically, because the particle is physically identical, except that it has a vertical velocity. It has a kinetic velocity through the medium, which is relatively stationary. Now the question is, what happens when that thing decays? Why is it not stable? And my hypothesis on that is that we also have to explain what a neutrino is. And in my view, a neutrino is just a very, very short type shock wave through the positron-electron sea. Kind of like if you hit an end of a row of billiard balls, you hit at one end and the energy goes through the balls and kicks out the other one. That is what I see as a neutrino. So that can carry energy to a very specific particle. And what happens is, the reason why it takes so long for a neutron to decay is because it actually has to run into one of these neutrino waves. So what happens is that the neutron contains a positron and electron. It has to get hit head on with one of these neutrino waves, which then causes one of the positron electrons, which are free in the sea, to actually join with that moving neutron. And then what you have is you have 3 protons. You got 2 protons and then 2 neutrons. Now the two protons and 1 electron will form a proton. See, this is what happens when you decay neutron. You get a proton, you get an electron. And this is what actually happens, that the object that comes out of the atom as a neutron actually has to gain mass in order to produce the neutron decay we see, which is the proton and then the free neutron. So that is how this is how I explain what the medium is, what the neutron is, what the neutrino is. They're actually all related. But inside the atom, the neutron is totally stable. So, but that's a very good question.
Yes.
Yes, Cameron.
Hello. Hi. Thank you. So, my question, my two questions. Number one, it seems the word glue is very important in your presentation. What is the material playing the role of gluing? Number two, is known that the mass of an electron is 1,360 of a proton. How will three electron or positron come together to make up the equivalent mass as a proton?
Okay, so the main question you're questioning here is that given the mass of a proton, you know, if I'm saying it's made out of just two positrons and electrons, its actual weight should be like, you know, 3 versus 108, 1,800. If you think about that kind of naively. So how do I get that? Well, you have to think about what mass is. Now, mass is not actually a measure of a quantity of something. What it is, it's resistance to being pushed through space. Okay, now I'm saying space is filled with charges. It's filled with a positron, electron, C. So all of these charges are going to try and grip to each other. So it's a matter of why is it this group of three objects is like, it takes over 1,800 times more energy to push that group of three through than it does to push a group of one through. Now, I would say that it's the analogy that I come up with is like, let's say you take a cube, and you've got a block of foam that exactly fits into that cube, right? So it's very easy to stick that first block in. Now, try and stick the second block in. So you jam that in there, it's going to be a lot harder to jam that in there, more than twice as much. Try and stick a third foam block in there, and indeed, it could take 1,800 times more energy to jam that into that same space. So it's the force is non-linear. But that's kind of an analogy just to show you that it may be very easy for a singular electron to get through this densely packed C. But to get three of those objects through that densely packed C might be like shoving those 3 blocks of foam into that same space. It takes tremendously much more energy to make it happen. But you know, fundamentally, you should not confuse mass with the quantity of things. Now, you also mentioned the glue, which is you'd have to be talking about what is the fundamental force between a positron and electron that makes them attract. And I simply explain that as an interaction of phases. The only difference between a positron and an electron is that they are resonating, and they are resonating out of phase. So they're doing something like this. But one's going in, one's going out, and between the two, the waves between them will cancel, creating a region of low pressure, and therefore the particles will be shoved in together, creating force of attraction. But if they're going at the same, like 2 electrons or 2 positrons, the waves will add, creating regions of high pressure, causing them to repel. So that's the basic glue of why the electrostatic force would work.
The structure you have there,
Yes.
is it a neutral body? The charges will form a neutral body?
Well, this is actually helium. This has got 2 protons, 2 electrons, 2 neutrons. This is helium. It's a cube.
Helium. If it is an atom,
Yes, this is an atom. This is the atom helium.
Helium atom.
Yes. This is what the helium, if you could...
Would you get the same amount, same kind of radiation from helium atom from this model?
what kind of radiation are you referring to?
Oh, there's radiation from helium atom. If you have helium atom in this structure,
Yes.
will it give the same kind of radiation?
Compared to what?
Will you get radiation from such a structure?
If it's just sitting there, no, you wouldn't get any radiation. It wouldn't be doing anything. It's just a bunch of charges held together.
Unless you're talking about thermal. Are you talking?
Yeah, are you
Moosa,
talking
are you
about thermal? What kind of radiation? Are you talking about radio waves?
No, thermal radiation. Say, for example, the discrete frequencies of radiation from atoms.
Well, thermal radiation doesn't come from atoms. Thermal radiation is atoms. If the atoms are moving around and hitting each other, that is thermal radiation. I don't think just sitting there by itself, it would radiate anything but a mild electrostatic field.
It seems to me more the arrangement we have here is more likely to explode.
Why would it explode? Why do you think it would explode? This is the question I want to ask you.
Well, the charges will be repelling. Some will be repelling, some will be, there may be an overall repulsion. And they will not stay together.
Well, you notice we have the alternating black and red squares. And if you do the calculations, you will find that, yes, this is an all-attractive construction. In fact, this is basically the lowest energy construction. This is a stable, if you model this in a computer program, this is a stable configuration where all the negative charges are only touching positive charges, and all the positive charges are only touching negative charges. So in that way, it is in fact completely stable. You don't have to do any magic to do that.
Yeah. No, Franklin, do you have the other drawing? Because we can't see into
We
this.
can't hear you.
Yeah, just,
Are you having a problem hearing or seeing?
No.
No, I'm saying it, you had another drawing with the circles.
Oh, you mean you want to go back and say this one?
Sure, because the one we can't see the colors, can't see the Legos or anything, but this one is very clear.
Yeah, here we have I've broken it down into the individual positrons and the electrons. So these two positrons are glued together by that electron, so they're happy, along with this proton. And then these two positron charges are being glued together by this electron, so they're happy. So it's just this big chain of negative plus, negative plus, negative plus, negative plus. So it should be intuitively obvious that that is a stable construction and will not fly apart. Yes?
I was under the impression that Gelman's theory was proven both for the proton and the neutron, that each had 3 particles in it.
Well, that would be quark theory, which I think is a lot of hooey. I mean, we have, quark theory is quite well developed and all that business like that, but we have actually yet to experimentally see a quark in isolation in any way. And, basically they've ruled out being able to see such a thing, which is convenient for them, which means that their theory can never be disproven. But I think ultimately it will be proven to be wrong. So.
Well, the question,
Can we have a microphone, please?
the question is, evidently there is evidence, if I'm correct, that the proton does have 3 little things in the bag, and
Yes,
that the
I believe that.
neutron has 3 little things in the bag. So what I'm asking you is, how do you deal with the information that they have evidence that there are 3 items in the neutron bag?
Now, I have studied this extensively. Now, definitely there's scattering evidence to show there are 3 centers in the proton. However, the same is not true of the neutron as near as I can see. The neutron is very much harder to study because you really can't study it in isolation, because it's kind of hard to grab hold of a neutron versus a proton. Proton, you can manipulate magnetic fields. Neutron, you have to observe it along with inside of some atom, and you have to make a lot of assumptions. And when I dug and I dug and I dug to see whether I could find the equivalent evidence for the neutron having three things, I could never find it. So from my standpoint, I don't believe I have found, I have not seen, I've asked people, you know, what's this evidence, and that they've not given it to me. So my supposition is that what you've heard about the neutron having three parts is simply unsupported and false. That I believe that based on that, it's just likely to be made out of 2 parts or 3 parts. But once again, you know, that's a supposition on my part. Perhaps this is an area where we could present an actual nuclear physicist with this hypothesis, and they could determine whether this neutron thing really is just a positron electron kind of thing, or whether it is, or whether it contains these 3 things. Now, you know, the evidence that Bill Lucas brought up recently was that by looking at the various isotopes and the energy budgets, we can tell that the only force that's really inside the atom is apparently 1 over r squared. If there was some mysterious strong force, it would have to be different than 1 over r squared. It would have to be like 1 over r cubed or r5 or something. And if that was there, that would show up in the energy budget. But apparently it doesn't, to the degree of accuracy required to tell that. So if these quarks are held together by some mysterious force, it's just not showing up, which is kind of another bit of evidence against quark theory. Because certainly what you're bringing up, which is that, you know, this is totally against quark theory. If I present this against someone who has quark theory, they say, no, neutron has 3 pieces, blah, blah, blah. Proton has fractional charges, not whole charges. That they would immediately bring that up. But I would think that this is actually a much simpler picture. I mean, it's really complicated to have these 2/3 charges, you know, plus 2/3 charges minus 1/3 charges minus 1/3 charges equals 1 charge. That's pretty complicated versus plus 1 minus 1 equals 1, right? And so there's really this total lack of evidence that I can see for there being these fractional charges. Yes, David?
Yeah, I'd like to comment on the quarks. There's quite a lot of us who have been working many years on showing that particle physics in general, from like 1930 on, is really a problem of people bashing things together, pretending they find signals, knowing they have to find signals because they spent a lot of money on it. Who you may want to look at, very good in this area, is Dr. Alexander Unsker. He's a physicist from Germany, and he's been fighting this a long time, like the Higgs fake. And many of us think we have to just pretty much start at the neutron, proton, electron level and start over. Now, the reason things get symmetrical is because they work them in symmetrical. Started out with 3 quarks, then 6 quarks, then 9 quarks, then 6 quarks. It took over 900 people to sign a paper. You know the papers in our book that we have? Usually they're authored by maybe up to 3 or 4 people. This had almost 1,000 to find the top quark. And the reason was they're not finding it. But if you get enough people together and say you're going to find it, you're going to find it. 6 months later, sure, they found it. So my suggestion to you is that just because they say they have signals, that is in many of our minds it's not really valid, because the entire system in which they're finding them is very flawed in our opinion. So that's just to give another idea. And like I said, they're going to make them symmetrical. It's going to look nice because they have to, but they've massaged it into that. So,
okay, I'm going to put someone on the spot here, because I know someone down here has an alternative atomic model which is incompatible with this one. That would be Mr. Lucas. So surely you must have some strong objections to this. So I want to hear what your strong objections are. Get the mic.
Wait a minute, you're asking someone to pick on you?
Yes, that's what we're here for. I want to be beat up on because.
Where's our judge? Can we overrule this?
I'm going to complete.
That's the real Franklin, yeah, that's the real Franklin.
I'm going to appeal to the Fifth Amendment since he's my roommate.
Wait a minute, you're driving him, so you're okay. If he was driving you to the airport, then you may have a problem.
Right.
No, go ahead, Bill. I know you have very specific objections, and I can't explain that unless you give them to me.
Well, you need there's a lot of atomic data, nuclear data, elementary particle data, and you need to find an explanation that accounts for what we see. And for instance, in elementary particles, my definition of what is a true elementary particle is if you cannot get the elementary particle made and form a beam of it and perform experiments with it, even though it has a very short half-life.
Now, Bill, I'm going to stop you right here because I know you love to go on and on with long stories, and I believe I've heard most of them. But I just want to hear, specifically what's wrong with this. So if you could try and get to the point, things will go faster.
Well, my kids love Legos, but I don't think that atoms and elementary particles are cubic.
Okay, that's a good start. So you don't think that atoms will form this kind of cubic structure, right? Okay, that's a reasonable objection. And I was kind of wondering, so why would you not think that they would form a cubic structure?
Well, most people don't think that the round particles can form a cubic structure. They expect some other kind of geometry than a cube.
Well, maybe you're just objecting to the fact that I had to model them in Legos because that's the only software I had. If those were round little balls, would that be better?
Then more people would accept it, and so I think there would be less of a problem. But the orientation that you get when you put together atoms and molecules and bigger things, usually you're displaying with the Lego structure, and it's hard to explain it that way you're doing it with round things.
Well, so I brought up some other, because this is the general question of, I've only showed you helium. Eventually, what does this thing grow to? And so I've shown some progressions of, as you're piling these things on, what they look like. Now, eventually, they get to something that looks like what I have here, radon. And basically, every different color represents one line in the periodic table. So these would be the outer nucleons, and in the middle, then in there, packed in the center, is actually the helium nucleus. Is how that happens. So this is the overall shape that you get, and I had to do this in order to match the ionization data that we get from the atom itself. So do you have an objection to it being this octahedral shape?
Well, in scattering, we can measure shapes to some extent, and I think that most people who do those scattering experiments would think that they would see that better. For instance, an electron can actually be seen in an atom, and you can see the toroidal shape of the electron. And so if we could see that, we could see much more in terms of the nucleus, you would think.
Well, this is my paper. So this here is a picture of a placer gold crystal. And if you look at it, it has an octahedral shape. Now, if you're familiar with crystallization, typically the macroscopic shape of the crystal is reflective of the microscopic arrangement of the crystal. And the fact that these crystals come out to be octahedral and looking a lot like this thing here, I think is kind of indicative of the microstructure that might actually be there. And there's another interesting piece of data, which is a scanning electron microscope here. This is really small on the screen here, but they've been able to image individual silicon atoms. And so this is the individual silicon atom that they've imaged, and it kind of actually looks like a Duplo Lego block. It's got like this big lump in the middle. It's kind of like boat shaped. You know, it kind of maybe looks like this thing, which is the silicon atom, placed on its edge like that.
Could it be that you're symbolic that the shape of the Lego is not as important as the position where things are?
Well, certainly it's about the positions. You know, I'm kind of limited in how I can arrange things, but the primary thing is not specifically this, but just the idea that everything is built out of protons and neutrons. They build out to these more complex structures. But I'm just trying to see what objections people have to the plausibility of that being the case versus conventional mainstream, which is that all the protons are all jammed together in a tight nucleus, tiny nucleus with the strong force and having electrons flying around it. So that's another, I didn't specifically mention it, but when I showed you the helium atom, the electrons are stationary in that atom. They are not moving. They're not orbiting. They are, in fact, kept in a static position when the electron is in its ground state. Only when you excite that atom will you knock the electrons out of the atom, and then they start doing their spectral thing. So that's another big difference in that all the electrons are kept inside of these structures here. You know, it's just they're all embedded inside, and they're not loose. There's no orbits. What we commonly think of as a shell, electron shell, actually refers to the varying distances you can see from the various nucleons. So like this orange part here, that we see that as basically one shell. The green part would be another shell. The red part is another shell. But you see you're just drilling into going from outside in. That's what gives you the different energy levels, not that the electrons are in any way orbiting or just kind of being held out into space. They are actually built on a scaffolding, and then they have a place in the scaffold, a solid place. Yeah.
What you've just raised is fascinating, because it raises the question of what is the scaffolding.
Yeah, the scaffolding is what I just showed you, which is a proton-neutron scaffold, which holds these electrons in place.
Try this on. You've got particles in the atom that are much smaller than the total size of the atom. At least from anything I've read, it appears that the atom is much more space than it is solid things that form the atom.
Well, that would be another completely giant miss on the part of science, in my opinion. So, for example, what I'm showing here is not the atomic nucleus. What I'm showing you here is the actual total diameter of the atom. So, and that is not 99% empty space. It fills the entire space. Like I showed you this picture of the scanning electron microscope picture of silicon. So this is a field of silicon. And if you look at it, you know, these look like edge-touching blocks. That does not look like 99% nothing to me. That looks like 100% space filling to me. So that is another thing that I believe is wrong. We get that from Rutherford. I mean, Rutherford went and he shot helium nucleuses that had gold foil and somehow concluded that the nucleus must be this tiny positively charged speck. And I believe, you know, if you read my paper, you would see why I think that's completely wrong.
Okay,
and the atom is actually space filling.
So you reject the idea that an atom is comprised mostly of space.
Yes, I would reject
All right,
it.
now, I understand that. I'm not sure that I agree with what you draw from those photographs, because there's a lot of space between the solid parts, and the solid parts may not be solid at all. They may appear that way because we can't get finer photographic work done. But in any event, the point I was making, if there is such a thing as scaffolding, might that totally change the concept of an atom and allow, for example, you to put the electrons in specific places rather than this amorphic cloud or orbiting
Well, I think
electrons.
that's exactly what I was just trying to explain.
Yeah.
That is exactly what my cubic model, atomic model is trying to do. It does totally change. I mean, like I said, I'm a dissident scientist. If I tried to explain this to any real mainstream scientist, they would immediately show me to the door. But there's the possibility that this is right, because, you know, it kind of holds together. So I think we have time for maybe one more question.
Hello, Franklin. In your previous paper, you talked about spin. And your positron, electron, each spinning out of phase and all of that. How does that play into the structure here?
I don't believe it does, so I'm not quite sure which you think you're referring to, because generally speaking, I believe that spin is not actually a inherent property of an electron. That spin is always measured on a silver ion, which is this gigantic conglomeration of protons and electrons, and that spin is actually a property of silver ions and not a property of electrons proper. And it doesn't really play into this model at all.
Okay, sorry, misinterpreted.
All right, so I believe that will do it for my speech.
I
Thank
just
you for
just
your
one real quick question.
question.
I noticed you have these sort of charts. They remind me of these four people and the charts they have made for atomic structures. And I was wondering if you've looked at them and consulted on them. James Carter, Stoyan Sarge, Ginsburg, and Lucas. Have you seen they have some periodic things that look like this, you know,
Yes.
and again, I'm not here at all criticizing or say they're right or wrong, but they seem very, you know, when I've looked at these books for many years, they seem very similar to your Lego type of configurations. Have you consulted those four?
Yeah, I mean, I've had James Carter's book, and actually his conception is very close. It's basically you take my model and you flatten it. It's basically James Carter's thing. You look at James Carter's stuff, it's got that same X format, is what it does. I mean, like I said, the only difference between him and me, I go in 3D. He flattens the whole thing out. But there's a lot in common between us. The reason why his stuff works is probably the reason why my stuff works, but I think it's just more likely that it forms a three-dimensional octahedral rather than, say, a flat sheet. And you know, I looked at Lucas's models. You know, he has like some pictures of oxygen, but I would dare him to try and draw, say, a radium atom using his.
Oh, don't do that.
Because the electrons are still kind of hanging outside. Versus, you know, this is like 118 theoretically. This element here. See, I would dare anybody to draw a diagram of their atom that's that big. But it's trivial in my model to do very large atom like that.
Okay.
But yeah, I'm aware of them, and I still think mine is better. But
Well, that's
yes,
good. No,
I
I was wondering if you did look at them. Okay.
Yes.
All right. Thank you very much.
All right. Thank you.